The mine body used pressed steel construction. Wall thickness averaged 2 millimeters. Internal volume prioritized fuse accommodation. Explosive cavity accepted cast amatol charges. Charge mass varied by production batch. Average fill weight measured 5 kilograms. Explosive casting occurred in controlled sheds. Cooling time exceeded 6 hours. Shrinkage voids required manual inspection. Rejected castings returned for remelting. The baseplate supported multiple fuse sockets. Socket threading followed inconsistent standards. Pressure fuse used a spring-loaded striker. Spring tension varied between contractors. Tolerance drift caused unpredictable activation loads. Specified activation pressure exceeded 300 kilograms. Field measurements showed lower thresholds. Temperature altered spring elasticity significantly. Cold weather reduced striker travel distance. Lubricant viscosity increased under frost. Delayed striker movement caused partial ignition. Partial ignition increased explosive fragmentation. Fragmentation threatened friendly deployment crews. Tilt fuse added lateral sensitivity. Tilt rod length exceeded mine diameter. Rod deflection translated into cam rotation. Cam rotation released a secondary striker. Secondary striker shared clearance with pressure assembly. Clearance overlap produced mechanical interference. Simultaneous loads jammed both strikers. Jammed mechanisms produced inert mines. Inert mines required manual neutralization. Manual neutralization lacked standardized procedures. Magnetic influence fuse occupied central channel. Magnet assembly used Alnico components. Magnet strength degraded during transport. As shock exposure demagnetized sensitive elements, magnetic fuse relied on vehicle mass flux. Steel hull composition altered activation reliability. Tracked vehicles produced inconsistent signatures. Magnetic fuse coil insulation cracked easily. Cracked insulation caused short circuits. Short circuits bypassed safety resistors. Bypassed resistors accelerated firing circuits. Acceleration increased accidental activation risk. Magnetic fuse arming required careful alignment. Alignment guides lacked clear markings. Misalignment reduced detection sensitivity. Engineers compensated by increasing magnet strength. Increased strength amplified mutual interference. Magnetic field affected tilt cam springs. Spring bias shifted under magnetic influence. Pressure fuse striker contained ferrous steel. Magnetic attraction altered striker resting position. Altered position changed activation. Threshold. Threshold unpredictability confused field manuals. Manuals contained conflicting load specifications. Revisions circulated without clear version control. Training units received outdated instructions. Improvised field modifications became common. Modifications included striker shimming. Shimming introduced additional failure points. Foreign material entered fuse cavities. Dust contamination impaired striker motion. Moisture ingress caused corrosion. Corrosion products increased friction coefficients. Friction prevented full striker acceleration. Incomplete acceleration caused low-order detonation. Low-order detonation damaged road surfaces only. Undamaged vehicles continued movement. Follow-on vehicles triggered secondary fuses. Secondary activation endangered recovery teams. Safety pins differed across fuse types. Pin diameters lacked interchangeability. Incorrect pins jammed safety sleeves. Jammed sleeves prevented arming conformation. Engineers relied on tactile feedback. Feedback proved unreliable under gloves. Night deployment amplified error rates. Blackout conditions restricted visual checks. Magnetic fuse arming required timed exposure. Timing devices drifted during storage. Battery chemistry degraded unpredictably. Degraded batteries failed during arming. Field replacement batteries lacked specifications. Voltage mismatches caused overheating. Overheating melted coil insulation. Melted insulation fused adjacent components. Fused components locked firing circuits. Locked circuits rendered mines permanently live. Live mines resisted disarming attempts. Disarming tools lacked adequate insulation. Insulation. Breakdown exposed engineers to shock. Shock exposure triggered involuntary movements. Movement disturbed tilt rods. Disturbed tilt rods initiated firing chains. Accident reports documented multiple injuries. Reports circulated through ordnance bureaucracy. Responses prioritized production continuity. Design revisions delayed by committee review. Committees debated single fuse simplification. Simplification conflicted with tactical doctrine. Doctrine demanded redundancy against countermeasures. Redundancy increased mechanical complexity. Complexity reduced field reliability. Test ranges simulated limited soil conditions. Clay soil masked pressure sensitivity. Sandy soil reduced tilt effectiveness. Magnetic testing excluded non-standard vehicles. Captured vehicles displayed unexpected responses. Engineers documented anomalies in appendices. Appendices rarely reached frontline units. Procurement contracts locked early designs. Amendments required renegotiation. Renegotiation stalled during wartime shortages. Steel allocation restricted redesign options. Alternative alloys increased cost. Cost increases met Treasury resistance. Treasury directives emphasized quantity targets. Quality assurance remained secondary. Inspection teams were understaffed. Sampling rates dropped below recommendations. Defective fuses passed acceptance tests. Serial numbers lacked traceability. Failure correlation proved impossible. Logistics units mixed fuse variants. Variant identification relied on paint marks. Paint degraded during storage. Faded markings caused misidentification. Mismatched fuses entered single mine bodies. Mixed assemblies behaved unpredictably. Documentation failed to track assemblies. Field engineers improvised compatibility checks. Checks slowed deployment schedules. Delayed deployments disrupted defensive planning. Commanders reported inconsistent minefield effectiveness. Effectiveness metrics conflicted between units. Statistical analysis lacked standard definitions. Reports conflated detonations with vehicle kills. Engineers requested controlled trials. Trials postponed due to range congestion. Congestion resulted from parallel weapons testing. Alternative mine designs entered evaluation. Simpler pressure-only models showed stability. Magnetic-only prototypes demonstrated selectivity. Tilt mechanisms proved most accident-prone. Accident data accumulated steadily. Data review lagged operational use. One design authority hesitated to withdraw stocks. Withdrawal implied production admission failures. Admitting failures risked political scrutiny. Scrutiny discouraged candid reporting. Lessons emerged gradually through attrition. Subsequent designs separated fuse functions. Isolation reduced mutual interference. Standardization improved training outcomes. Legacy mines remained in depots. Depots stored mixed-condition stockpiles. Post-war clearance teams faced unpredictable hazards. Hazards traced to compounded fuse complexity. Engineering doctrine shifted toward simplicity. Documentation emphasized single-trigger reliability. The problematic mine influenced future standards. Standards prioritized predictable kill mechanisms. Bureaucratic experience shaped ordnance philosophy. The design process recorded hard-earned constraints. These constraints informed later British mine success.